Okay, welcome to another Orbiter 2010 video. And in this video, I'm here on the moon at Brighton Beach. You can see the Delta glider landed there on the landing pad. In this video, what I want to do is a video explanation more so than the mission, like in a lot of my videos where I kind of do a complete mission where I go from, the Earth, out to Mars and land at Olympus, or, go to Earth to Phobos, or whatever it is, whatever the mission is. This isn't going to be a complete mission. I'm not going to worry about the fuel planning and all of that part of it. What I want to do here is just describe or explain how to do a certain task. And let me just briefly kind of go back. When I first started recording Orbiter videos, however long ago it was, I think it's been close to 3 years now, my motivation for recording the first video was because I was learning things that were somewhat difficult for me to just retain, for me to remember. And I thought that the easiest way for me to be able to get that information again would be to just record myself doing it. And then if I forgot how to do it, 3-4 months later, I could just go back and watch my own video. It turned out that that was really helpful. And I found that just by making videos of myself doing things in Orbiter, I was learning really, really fast. And it also gave me this great catalog of data to go back to. So if I ever took some time off of Orbiter, 2-3 months or whatever, if there's anything I forgot, I could go back and watch my own video. Now that's kind of what this video here is that I'm trying to make now. It's inspired by that same idea. Let me take a sip of water. A couple months ago, maybe 2 months, maybe, has it been 2 months already? I think it's been about a month. I was talking to Dimitri through Skype calls, and he was showing me how to do this very cool idea where you can start off on the moon, and then you can drop down to Earth and basically do like a gravitational sling at Earth and then go out to another planet. It could be Venus, could be Mercury, could be Mars, just anywhere. And it's very cool to do this because normally an injection burn from Earth to Mars is going to be like 3,600 delta V, something like that. But if you start off on the moon and you fall back to the Earth, by the time you get back to the Earth, you're traveling so fast that you only need an additional delta V of 350 to 450, 500, something like that, to go to, say, Venus or Mars. So it's a very cool little trick. But it's involved. It requires several steps. And I want to remember how to do that. So last night I practiced this. I did it 2 flights, and I felt like I now have a firm enough grasp on this to actually make a video that I can refer back to myself at some point in the future if I forget how to do this. So hopefully that intro explanation wasn't too boring for you. But let's switch camera views here. Now we are on the moon, and the first thing that we want to do is set up a trip to somewhere. Doesn't really matter where, but in this example I'm going to use Venus. And then I'm going to probably do 2 or 3 examples. Going to do Venus, going to do Mars, and maybe another planet. So for that part of the setup, anybody that's familiar with transects should be able to do this in a zip. We're just going to come over here. We're going to go to Escape, Forward. Now this is the Earth plan. We need to escape Earth, Forward. And for this example, again, we're going to use Venus. So there we have Venus, and if we want, we can go forward again to create that last stage. Now what we need to do is we need to figure out how we're going to go from the Earth to Venus. Even though we're on the moon, we'll worry about the moon to Earth part later. We actually have to start this planning kind of in the middle, which is what makes it a little bit more difficult than some of your other standard planning. And the way we do that is we actually have to turn on the advanced options. You can't set this up by using the default options in transects. It's just not geared. It's not geared for this type of flight. So I believe if we hit minus VR, we can go to advanced and turn that on, and then var gets us over to auto plan, and we can shut auto plan off. Now for cruise for plan type, I can't ever remember which one it is, so I have to just go to the plan option, and what we're looking for is the eject plan. So, okay, that's plan type is cruise plan, so we don't have to change that, and we just need the eject plan. Now we'll hit VW, and that brings us over to view eject plan. Now we can set up, here in stage 3, we can set up our Earth to Venus part of our flight. And we know that that's going to require negative prograde. I'm not going to actually do the negative prograde because I'm using the newer version of Transx, which has that auto min capability. So I'm going to take advantage of that. So I'm going to set the prograde to auto min. And now all I really have to worry about is the date. Note that I'm not setting the plane change. And there is a good reason for that. Basically, with Transx, it's a little bit more involved if you have to include plane change into this. So for these examples, there will not be any plane change. So just make sure if you're trying to follow along that you don't have any plane change at all. None. 0.00 plane change. So once we have the prograde set, we're going to leave auto. We're going to leave outward off for now, and we're going to start trying to find a date just by using prograde and date here. So I'm going to press ++, and we can see here, right around this date, that it's not good. So we're just going to go forward. And I'm going to go to the rough setting and speed that up. And all I'm looking for here is just a standard trip over to Venus, nothing fancy about it. And I'm not even going to be really particular about about the delta V cost or the time of flight. I'm not even going to worry too much about that because in this example, I just want to show how this trip works, how you go from the moon down to the Earth and then out to a planet, because it's very cool to learn that. And you can fuss over the details of time of flight and all that on your own. So we're pretty close here, it looks like. So let's go to a course setting and put in ++ and just watch our date come down. Watch our closest approach come down, rather. And it looks like we're pretty much there. Let me go to a finer setting yet and just kind of dial it back and forth there a little bit. Yeah, it looks like right about here we're pretty much slamming straight into the planet, so that works. Now before we go any farther, the first thing we want to do is we want to set our time in the simulator to 30 days prior to this date. And the reason for the 30 days, take a sip of water here. The reason for the 30 days is because that's about how long it takes the Earth, or rather I should say that's about how long it takes the moon to go around the Earth one time. And we'll get a more in-depth understanding of that here in a moment. But bring up the scenario editor and go to date and just put in the date that you have over there on the eject date, 571, and then minus 30 days, which would be 32. And then if you want, you can put in the decimal points. It doesn't matter. Apply, done, close. Actually, I should probably have left that open because we'll be playing around with the date editor a little bit more. We can see when we move that forward, the closest approach is a little bit off now. So if we want, we can kind of just here at the super setting, just press ++, and you can see that with the auto minimization, it pretty much just takes one click and it has you slamming into the planet again. If you need to, you can go down to an ultra setting and go back and forth as needed to bring your closest approach down so that you're actually hitting Venus. So now we have that part set up. Now what we need to know, what we need to figure out is when we can actually leave the moon. Because if you think about it, if you think about the moon orbiting the Earth, if we're going to drop down to the Earth and then basically kind of do a 180, almost like in Star Trek where they do that slingshot around the sun and they come out the other side. If we're going to go down to the Earth and then sling out the other side, we want to sling in toward the sun because we are going to Venus. It's pretty logical. If you think about if the moon is basically like on the outside of the Earth, if the sun is like me, I'm the sun, and the Earth is my fist, and the moon is here. If we drop down to Earth that way, we're going to sling around the Earth and then we're going to go out into the solar system. We're going to go farther out, like towards Mars and Jupiter. So we need to make sure that the timing is the other way around. we need to make sure that the moon, which is my finger here, is on the inside between the Earth and the sun, so that when we drop down from the moon and sling around the Earth, we go back in toward the sun and not out. The way we figure that out, we come over here to our stage 1 on the left side, and probably a little bit of maintenance we can do here first. Let's switch to VW escape plan, and let's make sure that we set our PE distance to 20 kilometers above the surface. And there's a reason for that, and I'll get into it in a moment. But make sure we take care of that. And 20 kilometers above the surface, of course, is 1758 E3. And if you put in the E3, that's the same as 000. So now we have the PE distance set accordingly. Now we're going to go forward to stage 2, and we're going to view over to the setup. And we need to do the same thing here. We need to turn advanced on and turn the auto plan off. And the fastest way to do that is press -VR one time, and that takes you to advanced, and then turn that on, and then var to go over to auto plan. I've found just by, if you go forward through the variables, it just takes longer. If you do it this way, if you go backwards and then forward, it's the fastest way to do it. So now auto plan's off. Now we're going to go to plan type. And I believe for this one, I think I actually remember it's initial. And then the plan is going to be escape this time. Yeah. So now we're going to press VW to view the escape plan. And the first thing we want to do here is, again, we want to set our PE distance to the PE distance that we think we're going to need around Earth, and that's going to be about 200 kilometers. So before we go any farther, let's set that up. And the reason that we need to make sure that we have the PE distance set is because you'll notice this perforated yellow or orange line. This perforated orange or yellow line will actually change slightly depending on how your PE distance is set. So we want to make sure that we get it set before we do anything else. So again, easiest way to do it, enter, erase all those numbers, and then we're going to put in 6571 E3. And that's 6.371, of course, is the distance between the center of the Earth and the surface. So by adding 200 to that, we're saying that we're going to arrive at Earth with an altitude of about 200 kilometers. We could go a little bit lower than that if we wanted, but we don't want to run the risk of getting too low, because then you're scraping the atmosphere and you're losing velocity, and we don't want that. So 200 is pretty safe. We'll go with that. And if you actually noticed when I pressed enter, you saw that shape change ever so slightly. In fact, let me just put in another number just to emphasize this point. 10.371 E3. And you can see how much that changes that shape. So by putting in the correct amount, 6571 E3, we have the shape that we need. And it's not necessarily the shape, it's the distance between here and here that matters. Okay, so once you have that set, then you can press VW. Let me see, what are we doing next? Oh yeah, VW over to setup. And we want to go to the scale to view option. And currently that's set to all, and we're gonna do there's a couple things we can do here. I'm gonna show you the way I like to do it. We're going to press ++ to bring up the target view. And the reason for the target view is this gives us this line right here, which you can't really see here. If we look really, really close, you can kind of see there's a line right there, but it's almost impossible to see it without actually zooming in. So by zooming in, we can see exactly where that line is at. And if we follow this line all the way across with our mouse, or if we kind of make a mental picture of it, we can tell that it's basically probably like right here, like this BCK button. It's probably halfway in between there. So if we kind of zoom out, we can tell that line that we can't hardly see anymore would be basically right about there. And what that is, that position is the antipode of, it's the antipode position of where we need to be when we drop back to Earth. It's, in other words, we need to be at Earth's periapsis at that point, and the antipode of that point is over here. The opposite side of that point is over here. Now what we want to know is we want to know how far out in the future is that, because when the moon's currently here, and so how far away is that? We could kind of just do some rough estimations, and rough estimations are actually pretty accurate, or surprisingly accurate. So let's start by doing rough estimations. In order for me to really know where that line is at, though, it helps me if I use a line drawing tool, and I'll put a link to this down in the description, where I just use this little distance tool here, and I'm just going to draw a line. You can actually start here in the middle, out to the side, and I kind of over exaggerate it all the time to put that line there. Now I'm going to drag it. I'm going to drag it all the way across. And what I'm trying to do here is I want to have that red line laying completely over top of that yellow line, so that in a perfect world, you won't be able to see any yellow pixels if I get that line positioned absolutely perfectly. It doesn't need to be that perfect though. But that's pretty good right there. I can actually see one yellow pixel, but that's basically perfect right there. So this tells me where the other side of that is at. It tells me where the antipode is at. Now if I hit ++ and go back to this view, I can see clearly, visually I can see exactly where that's at, and I don't have to use mental pictures, and I don't have to try to follow it across with my mouse. I can see exactly where it's at. But you can see also that my rough estimate was pretty good. I said it would be about halfway down between the BCK button, and that's about where it's at. So you can see, just mentally picturing it, you can get pretty good on it. Now speaking of mental pictures, the other thing that we want to do now, we need to know again when the moon's going to be at this point, so that we can calculate a more accurate eject date. This eject date is based on, this eject date's based on what we found before, but this didn't include the fact that we were going to be on the moon and have to fall back to the moon. Remember, this part of the plan is just the Earth, the Venus part. So now we have to refine. We now have to refine our eject date so that it includes this this trip from the moon back to the Earth. And the easiest way to do that is to actually just kind of eyeball this. You want the position of the moon to be at a 90-degree angle to this line here, and that's why it helps tremendously if you can actually have that line drawing tool and you can draw it across. That way you don't have to, it'd be a lot harder to visualize where 90 degrees was at without that line. But let me just fast forward time here a little bit and I'll show you what I mean. And as Dimitri was explaining to me, people are actually really good at estimating rough angles. We can't get it perfect. When we're looking for a 90-degree angle, we're not going to, most of us at least, aren't going to be able to eyeball exactly 90 degrees. But we can get really close, like 88 degrees or 91 degrees. We can be really close. And I can tell by looking at this that we're still not quite far along, quite enough. And I'm going to say that's about 90 degrees. And just by eyeballing it. Now what this tells me is that the moon is now 7 days away from this point. Because remember, it takes the moon 28.32 days to orbit the Earth one time. So half of 28 is 14, and half of 14 is 7. So a quarter of an orbit, which is 90 degrees. So from this point to this point is about 7 days. Now, just to test myself to see how good my visual guessing here is on the angle, I actually have an angle tool that I can use, that I don't have to use that stupid triangle anymore. And I can actually measure this just to see how accurate I was on just guessing where 90 degrees was at. So let me do that. Let me put this line down. Just give me a second to get it in position. About here. And we'll start, actually we want to start there at the moon. So that's one line, and then the other line's over here. And it's 92.10 degrees, and it's not quite perfect. I didn't even get those lines laid down quite right. But you can see it's 92.10 degrees. So you can see just by visualizing it, without even using measurement tools, you can get a really good idea, a relatively accurate calculation for where 90 degrees is at. And I'm going to have to pause this video because I have to take that call. Okay, sorry about that interruption there. Happens from time to time. So we know exactly, or we know now that the moon's position is presently about 90 degrees away from that point. So with that information, we can figure out when the eject date needs to be. 7 days from here to here, and then it's going to take us an additional 5 days to go from the moon to the Earth. So 7 plus 5 is 12. So from this date right now, that's this date up here in the upper left corner, we need to add 12 days to this number. And we can do that without even using a calculator or anything like that. So 57134, plus 12 is just 57146. Okay, so our eject date needs to be 57146.47. And we don't have to worry too much about the decimal points at this point because we're going to do another refinement. And I'll explain the reason for the additional refinement here in a moment. But again, 57146. So let's go ahead and set our eject date to that. And you'll notice when we do that, it's going to disturb this position, and that's why we have to do an additional refinement. Let's go all the way to course settings. So we're moving the date by several days. So we're going to go back to 57146. Get to that point. And again, we don't need to worry about decimal points here, so just whatever you get it there is fine. But now you'll notice that our closest approach is way off. We're not even, in our encounter view, we're not even showing up at Venus anymore, so how do we resolve that? Well, easiest way to resolve that is to now start using some outward. So we'll go to the outward setting and we'll put it on auto min for now. And then remember, no plane change. In this example, and in the following example, 0 plane change. So now that we have outward set to auto min, now we'll come back to the date and we'll go down to like a ultra setting and we'll just start tapping it a little bit. And you'll notice it has huge changes now that we're including outward in our calculation. And just by tapping it around a little bit, maybe go down to a super setting at this point. And if you hit this point where it's kind of hit a wall, what you can do is go to outward and check. And outward, unfortunately, maxes out at 1,000. And in some cases, 1,000 isn't enough, so you'll have to shut off the auto min and do it manually. In this case, we need more outward, so we're just going to add in some additional outward. You'll notice the closest approach is going up, but we'll fix that with the prograde. So let's start there. Now let's go over to plane change or prograde and take out some prograde carefully. And we're going to overshoot that a little bit, then go to the outward variable. And we're basically back down where we need to be, but let's just get it a little bit closer. I think I saw 11 there. Yeah, 6. That's good enough. If you go forward, you can see you're slamming into the planet. And now that's like the first part of the setup. But you'll notice again, as we did that, as we changed the eject date, it had a pretty significant impact on this shape over here. You can see that now this line that we so meticulously laid down is no longer halfway between this point and this point. It's now, it's off by a lot. So if we were to just try to use this plan as is, by the time we got over to the eject point, things would be pretty far out of whack, and it would require massive mid-course corrections. We could probably fly it, maybe. If we were going out to Mars, I'm sure we probably could, but going in toward Venus or in toward Mercury, timing's more delicate. So we might not even be able to make this flight work. So we're going to require some additional refinement at the very least. Now, it is getting close to 30 minutes. I think I lost track because I had to pause there. So I'm going to go ahead and end this part of the video here. And when we come back, we're going to do the next part of this setup, which is going to be refinement number 1. We might have to do 2 refinements. We'll see how it works out. If you like this part of the video, like it. If you didn't like it, don't like it. Subscribe to the channel if you're not already subscribed. Check for links down in the description below. I've got an FAQ, I've got a Facebook page, and all that good stuff, and I will see you in the next part.